Good afternoon here in Australia, and good morning to you guys over in Europe. We actually have people joining from all over the world, 330 registered attendees. So I'm actually pretty happy with this great turnout. And I am personally very excited for today's session because we have PVT royalty in the house. So welcome everyone, and thank you very much for tuning in. My name is Alan Mourgues. I'm a consulting reservoir engineer based here in Australia. I am the founder of CrowdField, an oil and gas subsurface community that fosters collaboration, product development, and freelance opportunities. I'm also the co-founder of GeoDataX, an AI-powered solution for smart data retrieval from private documents. And no, I'm not going to waste any time with boring promotional slides. If you're curious to learn more, feel free to just look me up on LinkedIn. There's plenty in my feed, and you'll find links to both websites there. So let's dive straight in. And today's topic is why do we do what we do in PVT? Now, it's my honor to welcome our presenter for today, directly from PVT powerhouse Whitson, Markus Hays Nielsen, whitsonPVT product manager. Markus is a reservoir engineer and PVT specialist. He's also a software developer and a prolific content creator. Markus is actually very active on LinkedIn, and he regularly shares insights packed with value. So if you're not already following the Whitson page, I strongly suggest you do. There's tons of value there, and it's indeed one of my personal favorites. So thank you very much, Markus, for coming today as guest speaker. I'm really looking forward to this one. But before I hand over to Markus, just a bit of housekeeping. We have 40 to 45 minutes for the talk, followed by 10 to 15 minutes Q&A. Please stay muted throughout the session. If you have questions at the end, please raise your hand with the little hand icon at the bottom of the screen and wait for my cue before unmuting yourself. Also, you can just type your question in the chat window if you prefer. And with Markus' consent, this session is being recorded for later distribution. Now, with all of that out of the way, let me just enable screen sharing and turning on the microphone. And Markus, over to you, mate. Take it away.
All right. Well, I'll turn all the stuff on now and get this up and ready. All right. Thanks for the introduction there. Appreciate it. It's first time I've been called a content creator. I guess you can see my screen. It's kind of fun to hear, I guess. I guess you stole my slide here in the beginning. This is just for reference for everybody. I'm not going to go through this again, but this is who I am, I guess. And then I just wanted, before we get started with the presentation, I wanted to mention that I'm actually doing back-to-back weeks of webinars. So if you're into this PVT stuff and you want to learn more about it, I have another webinar next week, which is going to be on the complexities of PVT data management and digitalization. So I just wanted to throw that out there before we get started. And then I wanted to give a quick disclaimer here. I think you said PVT royalty. That's kind of funny because my disclaimer here is basically that I don't know everything, and this is a good thing because nobody does, right? And I think it's something we can all admit to. I don't have all the answers, and I don't want this presentation to be me sitting here and telling you guys what to do and what not to do, because it kind of depends, and we don't know all the answers. And I didn't get here by myself. I've been very lucky to work with and read the papers of a lot of great people, different companies all around the world, that's really where I've learned what I've learned from the most, working with people, sitting down, trying to explain, trying to learn for myself. So I wanted just to give a quick shout out to all the folks that have helped me along the way. And I would be yeah, of course, my great team here at Whitson. You know, we're an ever-growing group of folks here in Whitson, and I wanted to give a couple special shout-outs, of course, to Curtis Whitson, who started the company, and he's also my dad, and I guess that's where the royalty part comes in. And you know, he's been an inspiration to me, and we've had a lot of good discussions. And of course, you know, Bilal Yunus is on the top left here. He's an unsung hero in the PVT space. He's the smartest person that I know, and yeah, I'm just very lucky to work with all these amazing people here at Whitson. So that's kind of a little bit of an introduction, you know, just get that out there. And then I wanted to highlight one thing, because it was actually pointed out in one of my LinkedIn posts, the difference between how and why. Okay, so we're going to be talking a lot about, you know, the topic is why do we do what we do, and so I just wanted to make this a little bit of a distinction, is that asking how and asking why are related topics, and it's kind of important to know the distinction here. And then on the left, one of the things is like, how does nature work? How does, you know, thermodynamics work? What is the phase behavior and stuff like that? How do we perform a PVT experiment? How do we measure a composition? And how can we ensure, you know, physical models? That's the how question. And then on the other side of things, we have the why questions. And then a good example of that is, why do we take fluid samples, which is something we're going to talk about here in a little bit. And also, why do we perform the PVT experiments that we choose to pay money for, right? That's the why type of question. And not all why questions are you know, worthwhile. One of them is asking, like, why does nature behave like it does, right? This is one of the critiques that I've that was pointed out here by Hassan on LinkedIn, that I made the distinction to say, you know, when we talk about thermodynamics, when we talk about why does, you know, two component system give us a phase envelope, but a single component system give us a vapor pressure line, right? In nature, we're trying to describe how, we're not asking why necessarily. So that all out of the way, let's get to it. And I want to start at the beginning of why we do what we do. And the first thing when it comes to PVT is we have to collect a sample, right? Sampling is a huge topic. There's a good section of a book that my Curtis and Sisson and Bilal here at Whitson wrote a while back, and I can probably share that if it's of interest to you. But I wanted to take kind of a very top level view of collecting fluid samples. And what I've done here is I just have a little bit of a schematic overview of what, you know, kind of a typical well in Oklahoma, where I was born, looks like. You know, it's onshore. You might have a vertical well because it has to be cheap, and a surface process like this. And so you got your perforations down in the reservoir. And there are multiple ways of doing sampling. Okay, one example would be to go down into the well and collect a bottom hole sample. Okay, so you're actually taking a fluid down in the reservoir in the well bore, right? But that's not the only place where we can do sampling. We could also potentially go up to the surface and collect a separator gas and a separator oil sample here at the very top of the well. And there are pros and cons of doing sampling, and there are definitely big variations in costs. And so we really should ask ourselves, what is the goal of doing sampling? And what I've tried to do here is to subdivide, you know, why we do sampling into two different parts, which are subtly different with two separate goals in mind. Okay, so on the left here, we have what I call fluid initialization. And that's basically trying to say, what's down there in my reservoir, what's in my well stream, right? And how can I get an estimate, a physical estimate of what is in my reservoir, right? And that is subtly different from this other side, which is the fluid model development. And the reason we do sampling for fluid model development is so that we can perform PVT experiments, right? To develop an equation of state model, preferably, and other auxiliary models like a viscosity model, wax and asphaltene models, and so on and so on, diffusion models, right? So even here, when it comes to collecting samples, there are different goals depending on what you're trying to do, right? And whether or not a sample is quote unquote representative will be dependent on what you're trying to do with that sample. So if we go back to our system here, and then we decide that, okay, for this specific system, I want to know what the compositional variation is versus depth, right? That's the fluid initialization part. Then I might have to do a downhole sample, something like this, an MDT sample, an OFT sample, something along those lines, where I can get a point estimate of the composition in the reservoir, okay? What we call an in situ representative sample. Then we take that sample and we transfer it to the laboratory. And once we take it to the laboratory, it might be sticking around for a shorter or longer period of time in something that we call, fluid storage, right? And the thing about fluid storage is that you're paying quite a lot of money to have those samples stored in the laboratory or in some sort of a storage facility, right? You're paying for the actual storage, and you're paying for the lease of the cylinder and maintenance, and keeping them pressurized and all that stuff. So because it's costing us a lot of money and we can have a lot of samples, this can be a real big impact on the economics of your development. So one of the things that we should think about is, why do we do sample storage, right? And one thing would be that you have to store it temporarily to do a set of initial PVT experiments, right? And potentially, if justifiable, you might also want to do some future experiments like, gas EOR or something else. And there might be other experiments like SCAL and other things where you might need larger volumes, or you might want to do it at a later point. But one reason why that's not acceptable for keeping samples around is just to have some just in case, right? Because if you have a pressurized sample, it can cost you thousands of dollars per year just to keep around. If you have 100 of them, well, then you're talking a lot of money per year, right? And so it's important to have a specific good reason for why you're keeping these samples around in storage, okay? Moving from the sampling kind of very quickly here over to the reservoir compositions, okay? I think everybody who's dealing with PVT knows that at some point we're going to need compositional analysis. But why? Why do we need reservoir compositions? And before we get into that, I want to emphasize something that I always try to emphasize, both on LinkedIn and in my courses and when we're doing consultancy work. Reservoir compositions are not measured directly. They are estimated, okay? And I'm going to very quickly go through that process of estimation for the bottom hole sample that we took here in the beginning. And this is a very important fact. If we take that bottom hole sample or that MDT sample to the laboratory and we ask them, can you please give me the composition of this PVT sample? Then what the lab will do is that they will take out part of that fluid, they will flash it to surface conditions, or at least surface pressure, and they might have slightly higher temperature. And then they will get a flashed gas and a flashed oil composition like this, okay? They will also measure some other properties, some recombination properties, like the recombination GOR, gas-oil ratio, flashed oil density, flashed oil molecular weight. And then they will calculate some properties, like the flash gas molecular weight and average molecular weight of the sample. Then they will take those flashed gas and flashed oil samples, and they will take those through something that's called a gas chromatograph, which will have a separate kind of detector for the gas phase, which will give you a molar composition for the flashed gas. And you'll have a separate detector for the flashed oil, which will give you a mass composition, okay? So this is the procedure that the lab will go through in estimating your reservoir composition. That's whatever's in that sample that we just took. And they will have to mathematically recombine on a mass basis, the flash gas and the flashed oil, using some equation. And then they will have to convert that mass composition to a mole composition using a set of molecular weights, which we don't know. Okay? So the end result that you get, typically in the beginning of your PVT report, for what that sample molar composition is wrong. It just is not going to be correct for multiple reasons and assumptions that go into making an estimate of that composition. Okay, so just have that in the back of your mind. Now, why do we need reservoir compositions? Okay, and here I'm also going to subdivide it into the same two parts as we did for why we do sampling, right? For fluid initialization, well, we want to know what's in our reservoir so we can calculate key PVT numbers like oil formation volume factor. You know, that's the reserves that we have when we're taking that reservoir oil up to the surface. And here I've written if representative. This is representative of what's actually in the reservoir. We'll talk more about that at the end. Or what's in my well stream. And then for the fluid model development, we don't care about what's in the reservoir necessarily. We only care about being able to describe the composition of what's inside of our PVT cell. Okay, what's in that tank that we're using to do the experiments on. And another reason why you might want to do compositional analysis is to do the mathematical process of decontamination if you have oil-based mud contamination. All right. So once again, we need to get a composition, but the goal is slightly different depending on if you're trying to do initialization or model development. Then we move on to the PVT experiment. So now we've taken our sample down in the reservoir, we've taken it, transported it to the laboratory, stored it, burned some money for a while, and estimated the composition of that tank, which might or might not be representative of what's in our reservoir. And now we're going to take that tank and do some experiments on it. And that's where this comes in. And it typically looks something like this, right? You have some CCE, you have some DLE, and this, that, and the other. But what I want us to do is just to think a little bit about why do we do PVT experiments? And I have basically here two statements, and I want you to think a little bit about what you think the reason is that we do these PVT experiments before I tell you. Okay? So the first option is we want to do a PVT experiment to try to emulate the reservoir depletion process. The second option is we do the PVT experiment because we want to develop an equation of state model. Okay? And I'm going to give you my perspective of it. The sole reason why we recommend doing PVT experiments is the second part here, to develop an equation of state model, not to emulate the reservoir depletion process. And why do I say that? Well, because the reservoir models that we have, reservoir simulation, or the surface process that we have, you know, with the surface process model, are going to be much more complicated than anything we can do in the laboratory with a very simple PVT experiment. So what I would much rather do is make a model that I know can describe the thermodynamics of my fluid system, and then use that thermodynamic model, which is hopefully consistently developed, to be put into those other softwares that can more accurately describe my reservoir depletion process. Okay, so that's what I wanted to mention on this. And then I want to take another kind of critical look, and this is a point where I don't necessarily know the answer of what's best here. Okay, this is something that we are, you know, researching at the moment here, is what PVT experiments should we choose, right? One of the kind of the traditional approaches is to say that, well, if it's an oil, then I should do a CCE, a DLE, and a multi-stage separator test. That's kind of that's been the traditional way of just stating it, that if you're going to do the full suite of PVT experiments, these are the experiments that you should do. The CCE to get the saturation pressure, the multi-stage separator test to describe the surface process, and the DLE is supposed to emulate the reservoir depletion process. Okay, but if you think about how the DLE works, then it basically is behaving like a reservoir with an oil relative permeability of 0. And I mean, I don't do a lot of reservoir simulation modeling, but very seldom do I see a rel perm of the oil phase being 0 throughout the depletion process of a reservoir simulation run. Okay, so it's not a real emulation of the depletion process, and therefore I don't necessarily think this is a good argument. Yeah, and this is if you're doing like gas EOR as well, then you would do a swell test. All right. So is there an alternative approach? And I'm just going to throw out some numbers here. You have the traditional way of doing things with a DLE and a CCE here on the right. And if we just take some arbitrary numbers here and say it costs $10,000 for a CCE and $25,000 for a DLE, okay? Just to have some ballpark numbers, this would cost us a sum total of $35,000. And you see that the DLE, because it's a more complicated experiment, it's going to cost more money. It's going to take more time for the lab to do. So let's see if we can think of another alternative here to how we can potentially do more with the same amount or a similar amount of money. Okay. So the CCE and the DLE are typically always done at the estimated reservoir temperature. But let's say that instead of doing a CCE and this more complicated and more expensive DLE experiment, we did 3 CCEs, one at the reservoir temperature, and 2 more CCEs on the same tank that we have, right? We just increase the temperature and redo that constant composition expansion experiment, okay? And if we increase the temperature once, we're going to get closer to the critical point. We're going to get the more volatile fluid behavior. And if we increase the temperature even more, we might actually go across the critical point over to a gas condensate behavior, okay? So what do we get out of these 2 different approaches? Well, if we look at the traditional approach, we're going to get a single saturation pressure point on this pressure temperature plot. This is our bubble point for that CCE that we did. And then we're going to get the DLE behavior. Okay, I'm showing the BOD here, so the differential oil formation volume factor, but we're also getting like the gas being removed or solution GOR values here as well. Okay. The alternative approach basically gives us 3 dots on our pressure temperature phase diagram. Okay, so if I took these 2 scenarios and I made an equation of state model for both of them, then over there on the right, I might get a extrapolated phase envelope, a simulated phase envelope that looks something like this, which describes this 1 CCE experiment and the DLE experiment. Whereas if I create a phase envelope for what's on the left there, I'm going to be much more restricted to what this phase envelope can look like. And what you will see here, that's kind of shaded in here as a lighter or dimmed color down here. And you can see you can have dramatically different phase envelope over there on the right to what we have over there on the left. Okay. So I'm not necessarily saying that the one is better than the other. I'm just saying that there are alternatives, and our question should be, why do we order the experiments? Well, we order the experiments to develop a model. Therefore, we should start thinking about which one of these approaches is going to give me more bang for my buck for developing my equation of state model. Okay, it's a very important question that's kind of an ongoing research topic that we're working with a lot of operators to try to figure out. And there's one super major who has stopped doing DLEs completely because they just don't trust the data, and they think this multi-temp is better. And I'm not going to say who it is, but they got some very strong opinions on it. So that's kind of an interesting thing. All right, so we've gotten to the point now. We've done the sampling, we've got an estimate of the composition, and we've done the PVT experiments. And we agree that, you know, the reason that we do these experiments is to develop an equation of state model. But then the question is, you know, how do we create this fluid model that we're looking for? And I just want to take a top-level view of a typical depletion or typical, field development process here outside of Norway, where I'm sitting. And you could have multiple fields commingled here, and going up to a platform and then being shipped to a surface processing facility over here on the right. And throughout this process here, we're going to have different softwares for the different segments of this field development. And all of these different softwares require basically a fluid model of some sort. And these fluid models can basically be categorized into two main parts. Over there on the left is what I would call like an EOS-based fluid model. And over there on the right, you have a black oil PVT-based fluid model. Okay, so a volumetric model. And the question then is, how do we generate the best fluid model for the system that we need? Okay, I'm going to run through 3 scenarios very quickly here and talk about some of the pros and cons, and then you can decide yourself, you know, what you think makes the most sense. Of course, I'll be biased because of, you know, our workflow, but that's up for you to decide. So one way of thinking about it is I want to develop a black oil table directly from my PVT data. This was the go-to standard in the 60s and potentially a little bit out into the 70s and 80s. Okay, so you take a sample, right, with all of the uncertainties that come with that, and you do a PVT experiment with all of the uncertainties that come with it, and you can use a set of correlations to generate black oil tables from that single sample with its PVT experiments. Now, the nice thing about this is that there's no advanced model required to do any of this. It's just very straightforward, very simple to do. The issue is that the correlations can be inaccurate. Okay, so very often in PVT reports, you'll see the DLE data and you'll see the corrected DLE data using some correlation, and then they say you can use that directly in your black oil simulation run. But the issue with that is if you do it compositionally and show, then you can actually show that it might not be that accurate. And it's also very dependent, it's dependent on that lab-specific surface process that was used to correct that data from like the DLE or CVD to an actual surface process, right? And it's going to be dependent on on whatever the lab chose to do their MSS for. And because it's a single sample, if there is some sort of laboratory measurement error, either in the composition or the measurement of the PVT experimental data, then that will be amplified here because it's only a single sample being used. Another alternative would be to take a single sample, take all the available data, make a lumped equation of state model directly, and then from that, you can generate black hole tables if required. Okay. The nice thing here is that it's very easy to match, you know, an equation of state model to a single sample because you have so many knobs to turn and there's very limited data for a single sample. That's also one of the downfalls of it. It's easy to overfit. It's very non-unique typically because there are so many knobs to turn and so limited data set. And this will result in when you get the new sample coming in, you will most likely have to remake your model. And so you're going to spend that, you know, the easiness of just making a single sample model, you're going to redo that process many times, and then you're not going to be able to have a consistent model for all of the different samples, all the different wells in a field, for example. The third example here, or third method, is that you take all the samples with all of the data that you have, you develop a very detailed, extended compositional model, and then from that, you create consistent lump models and black hole tables as you need them, fit for purpose models. The nice thing here is that this model will typically be more unique. It will highlight any data uncertainty in one or more of these samples because of both being able to match all the other data. So it'll highlight if one of them is falling off the trend and other things. You're typically not going to need as frequent updates or upgrades of the models or reworks. The issue is that it's harder to tune and you need the right tools for the job, right? So that's kind of the big downside of this part, okay? But another nice thing about this is that if you do this, what we call parent-child model development, then you can take that detailed parent model, generate a black hole table and a lumped equation of state model, which if you give them the same temperature and composition, they should have more or less the same PVT because they came from the same parent model, right? And the same thing if you use another lump model with different constraints, maybe instead of the flow assurance constraints, you might have the surface processing constraints, which might be slightly different. And throughout the field development process, you will have all these models, which will all come from the detailed parent model. And that creates this internal consistency. Okay. So our kind of recommended approach for this in the software that we have, whitsonPVT, is basically that you have a fluid model, which is built out of an equation of state model, a gamma model, and a set of auxiliary models like the viscosity. The equation of state model is built out of a lot of different components, individual molecules like the non-hydrocarbons, the light hydrocarbons, and what are called single carbon number components. They're not, yeah, we'll talk about this in a second here. If we zoom into this component slate, you see you have the same things here. And if we look at one of these single carbon number components, for example, C7, then you can see that it's actually made up of a bunch of different components, compounds, right? And they have very different shapes and very different parameters. So for example, benzene, even though it's in the single carbon number C7 group, it only has 6 carbon atoms. And normal C7 has 7 carbon atoms, and they have a dramatically different shape, which will have an impact on their critical pressure, critical temperature, eccentric factor, and so on and so on and so on. Okay. And the only reason why we need a different equation of state model for field A and field B, different parts of the world, is because of the difference in the distribution of these subcompounds that make up our C7 plus fraction, single carbon number components, like C7, okay? So like, let's say my field in Norway has slightly more benzene, and your field in Australia has more of the normal C7, the paraffinic components. Then a single C7 component property value can't describe both of our fields. So we're going to need to characterize or tune our equation of state to match those separately. All right. So with that equation of state model, we can take that together with a molar composition, and we can do a bunch of calculations and make a bunch of models with it. We can generate black hole tables, we can fit PVT data, and we can predict things like fluids in place. Okay. And then I'll just kind of very quickly go through this. The whole process of fluid model development, we have a whole course on it, can be a bit of a, you feel like you're doing a conspiracy theory because of all the different parts, but very top level here, you got the database, take that data from the database into the detailed model development, where you can generate the child models, black hole table, and lumped equation of state, which can then be used in the domain-specific software downstream of that. Yeah, and this is just the overview of this process. I'm going to skip through it here just to not take too much of your time here. But basically, you're trying to say what's inside of your fluid and how does your fluid behave, right? How does it change? This is our PVT experiments, and this is our compositional analysis and data. And then the very last topic that I wanted to talk about here is fluid initialization. And I'll try to be quick, but it'll be a little bit complicated here. And we already talked about this slide. So over there on the left, we're talking about the fluid initialization, and that's basically trying to describe what's in our well stream, what's in our reservoir, and how can we get to that composition, which is this last part called equilibrium contact mixing. Okay. And yeah, I'll do this one here. So when we're trying to describe what's in our well stream by looking at looking at the separator samples, there's some of the other examples that we were talking about. You can, in an ideal case, if you have perfect sampling, it's going to look something like this. Your fluid is going to produce into your test separator, and you're going to get a separator gas and a separator oil. You're going to measure some properties, and the goal is to estimate what the composition is that came into your separator, which you don't measure directly, right? You take this sample and that sample, you measure the target GOR, and then I'm just indicating the mass here, and then you're basically moving those to the laboratory and getting an estimate of the compositions of each one of those, which we now also know has some uncertainty attached to it. And if everything goes perfectly, then the amount of mass, or like what you have in the laboratory, was actually what you sampled in the reservoir, like this, which means that we can just mathematically recombine that separator gas and separator oil, and everything should be good. Okay. However, that's not always what happens. Okay, we can have non-equilibrium sampling conditions, or like what I'm going to show here in this case, we can have leakage from the oil sample, the separator oil sample, and what you'll see is that it looks just like before samples, right? Let's say that the sampling was done perfectly, but when I transferred my separator gas, all that went perfectly fine. But when I transferred my separator oil, at some point, I got a little bit of leakage coming out of that, okay? And I'm drawing it as a red arrow here because it'll typically be the light components in the gas phase kind of leaking out of the separator tank. So if we have this now, we're going to get the correct estimation of the separator gas composition, but our separator oil composition will not be the same as what we measure in the laboratory, or we estimate in the laboratory. Okay, that's kind of what I'm indicating here. And so we have this situation where the sampling went well, but the transport something messed up, and so the question then becomes, what do we do? Okay, how do we handle this? Okay, and remember, the goal is to try to get a good estimate of the well stream composition. The traditional approach here is that we make some sort of a QC plot, typically the Hoffman plot, that looks something like this. We're not going to go into what it is. And then we typically make a material balance plot, which is just looking for a straight line. Okay. Now, my question is, well, what if the Hoffman plot isn't a straight line? Okay, what if our QC doesn't pass? Okay. And then I have a couple of examples here. Well, one option would be we don't use the sample. Okay, we don't use that separator recombined sample for anything, or we can use that sample, which you know is in non-equilibrium, to do model development. And then the third option here is that we take that wrong set of compositions, put them together, and then try to correct them somehow to get the better estimate of the well stream composition. And my initial reaction here is that we should not avoid, or we shouldn't just disclaim this sample just because, right? We can still use this sample to develop an equation of state model, because the equation of state model should be robust enough to extrapolate slightly beyond the exact composition that we have. And there are tools called equilibrium contact mixing tools that we can do using a tuned equation of state model to get a better estimation of this composition here. And I'll show you one example right now. In the perfect sampling case, you would get your recombination ratio, which is just the part that you use to mathematically recombine the separator gas and separator oil. And you can do that mathematical recombination. And if everything goes well, then the lab estimated recombined composition should be the same as the well stream composition, and you're all good to go. That's the perfect sampling case. Now, if we have the leakage case, we do exactly the same procedure, but with the wrong composition here, the wrong separator oil composition. And so the mathematical recombination will also be wrong. And then we can go through this procedure of just reflashing it using our equation of state model, which is tuned to the PVT experimental data available, and do that mathematical recombination again. And kind of almost by magic, everything typically gets pushed in the right direction, and you can get a very accurate estimate of that original well stream composition that you started with. Okay, this is an example, and it was also presented in this SPE paper in Brisbane, actually, which was kind of nice, of this equilibrium contact mixing approach or methodology that lets you kind of get the good estimate of the initial fluid that you have, even if the samples that you take are not in equilibrium. Okay, So I think I'm running out of time here. Alan's nagging me here on WhatsApp, so I'll skip this last part and I guess just open it up for questions here. So if there are any questions, then yeah. But actually, let me just skip to this here, and I just wanted to quickly go through the conclusions before we do that. Yeah, we don't know everything. That's my first point here. And so what I highly recommend is go and find somebody who challenges you, who you can discuss with and try to learn from. And don't fall into the trap of just doing what's been done in the past, because that's what was done in the past. Don't be afraid to ask why, especially for young engineers. This is a very important thing. Yeah. So the third point here is that the same process, like when we talked about sampling, can have very different goals depending on what you're trying to do, right? The goal of sampling from a model development perspective is different from fluid initialization perspective. Okay. And another thing here is that what is reported in a PVT report is not necessarily what was measured, and it is important to understand and be aware of how this was generated. Yeah, and all the uncertainties that come with it. Sorry about that, kind of rushed on the end there. Went a little bit over time, but I'm more than happy to take questions now.
We have time, Markus. Thank you very much, mate. That was a great pack, clear messaging, fantastic schematics and animations, really cool. So actually, before opening up, I have a question of my own here. I think it captures the one questioner who raised his hand. And I like the wording you use to distinguish between, I think you use fluid initialization and fluid model development, if I got it, if the memory doesn't fail me. The question is, I think you did answer in the way you closed it, but basically my question was whether you can get to the second without the first one. In other words, if you happen to, for whatever reason, you didn't have an initial fluid composition, the field's already depleted and you take a sample, or the field was originally a dew point or a saturation pressure. Is there any value at all in performing a PVT analysis on a sample? And if I understood you correctly, understanding that distinction that you make, it is valuable to get an equation of state for fluid development from where you can basically back engineer the composition at original condition, if I understood you correctly.
Yes, exactly. And there's a great paper by Even Fairvang. I can link that to you as well, Alan, and you can send it out. That talks about exactly this approach. This is for reservoir compositions. What I showed was for estimating well stream compositions. But yeah, and the kind of the classic example is, well, what if I don't get around to sampling my reservoir until it goes under or below the saturation pressure, right? How can I get an estimate of the initial fluid in place, right? It's talked about in that paper. For unconventionals, like in North America, there's a lot of like shale fluids. There, it's actually not possible because you need such a high drawdown to do bottom hole sampling that you're going to go below the saturation pressure, and you're going to basically not be able to get an initial fluid composition by doing downhole sampling. So you can use this ECM approach for that. Yeah.
Yeah, great. Yeah, I'll reference that paper on the email with the video distribution. There are some questions popping up in the chat, but first I want to allow, sorry mate, but your name comes with, I think, Russian characters, so I don't know how to say this, but you raise your hand first. Go ahead, mate, just unmute yourself and fire away.
Yes, yes, hi. So you can hear me, right?
Yes.
Very nice. My name is Dennis, but it's written in Russian, so this can be a bit complicated for you. So first of all, thank you for presentation. It was very nice, and there are a few approaches, new approaches for me. So I'd like to ask you one more thing. Can we use the same approach with different CCEs for, let's say, gas or gas condensate reservoirs?
Yeah, and for sure. And what I would emphasize there is for the oil sample, I went up in temperature to get closer to the critical point. For gas condensates, my personal opinion would be to go down in temperature to get if you have a very lean gas condensate, for example, with a very small maximum liquid dropout, then if you go down in temperature, you're going to get a higher liquid dropout, which is going to have a smaller uncertainty in the measurement in the laboratory, and that will help you get a better match as well. Yeah.
So doing this, we can eliminate CVD test, right? More or less.
Yeah. So the only thing that I would emphasize here is that the nice part of the CVD test is that you're getting compositional variation by removing that excess gas from the top. Okay. But in some cases, it's actually not possible because the fluid is so lean to do a CVD test. So what we've done for consultancy work there is just recombined the separator gas, separator oil from the gas condensate field at multiple GORs and done the CCE at the same temperature but at multiple recombination GORs in the laboratory. And that would be an alternative to a CVD as well.
Oh, yeah, that sounds great. Thank you. Thank you so much.
Okay, I don't know if you can see the chat, Markus.
Yep.
Christina Golako is asking any advice on similar approach for CCE at different pressure and temperature for gas condensate field.
Yeah, and I think we just covered that. Basically, if you're going to do multi-temperature, I'd go lower temperature because you're kind of moving towards the critical point or kind of more of a rich gas condensate. But you know, we shouldn't completely remove this compositional aspect of a CVD. If you're gonna if you don't want to do a CVD for some reason, then I would recommend recombining that gas condensate at multiple GORs and doing the CCE instead. Yeah, I hope that answered your question. Yeah, good.
Yeah, there's another. Can you read yourself the questions on the chat, or do you have visibility, Markus?
Yeah, I see it here. So it basically says if we found the opening pressure for an oil sample is equal to almost 14.7 psi, what can we get from this sample? Just composition. Okay, so you're talking about a separator oil here. I'm assuming because if you have a bottom hole sample that goes from 200 or 300 bar down to 1 atmosphere, then you're gonna have I don't know if there's gonna be a lot of value other than there is gonna be value in that composition and that potential density as well. Okay, so I talked about this, trying to describe the character of these single carbon number components in the C7+ part of your composition, and flashed oil samples, produced oil samples, crude oils, they have many different names. It's basically just oils at surface conditions, right, that are produced from your reservoir, are very, very useful for two things: compositional analysis and measuring the flashed oil molecular weight and density, which can be used in characterizing your reservoir components, but also doing distillation experiments. Okay, the distillation experiment is the only measurement which will give you an indication of what that, how paraffinic or aromatic is your fluid for those different components, starting at C7 going up to, C20, typically in a distillation experiment. So definitely still useful, but not for, PVT experimental data necessarily, but compositional data, flashed oil data, and distillation experiments if you have enough volume. Yeah, for sure. Any more questions?
Great. Anybody else want to raise their hand? Take the mic.
Yeah. So we have a course on fluid model development. I don't know exactly when it is, and we also have its own course on gas condensates. But for unconventionals as well, there's probably going to be something in the US time. Yeah, I'll try to follow up with some of our webinars and courses that are coming. Yeah. Good.
Well, great. Anybody else? Sorry, I missed somebody. Okay. Well, I think we're just 5 minutes short. That's good. I want to Thank again everyone for joining. Please drop me a note if you have any comment, feedback, or suggestion for the next one. As I said at the beginning, this session has been recorded, and I will publish it on my YouTube channel for distribution. Thank you again, Markus. Fantastic talk. Great pack. Great.
Yeah, happy to help.
Diagrams and schematics. Loved it. And thank you, everyone. That's a wrap.